I know there's these quirky things about Zoom, and we were talking about that earlier. It's confusing sometimes. Then they fix one thing and then they mess up something else.
That's right. You get used to it one way and then they change it.
Yep.
It's like a classic.
Oh, I see someone from Colorado. I'm
Yeah.
in Colorado now.
Clark, Colorado. Where's Clark?
I'm not sure where Clark is.
Kansas City, Tallahassee.
Tallahassee, yeah.
Grand Forks, nice. Yeah, we were just having a chat right beforehand. We were comparing smoke and weather patterns around the country. Since we're in 3 different spots today. We can hopefully the skies are a little less smoky and nice and clear for you all. I'm about to get some wet weather myself, but at least it gets the smoke out. So Western New York. I'm in northern.
Yep, it's pretty smoky here outside of Boulder.
Oh yeah. Oh, I can bet.
Oh, someone from Loveland. Yep, that's not far from here.
Well, that big fire up in the Dixie fire is now well over 600,000 acres, which is
it's crazy.
And it's pretty much burned about a third of Lassen National Park. And so our good friend Kevin Sweeney, who has run the Lassen Dark Sky Festival. And so he's been dealing more with smoke and fire issues than with doing some of the interpretive things.
Was he a Dark Sky Ranger? One of the
He was
Dark Sky Rangers?
Yeah, he was one of the he went through the Sky Rangers program once upon a time.
Nice. I shouldn't say was, because you
Yeah.
always are. If you've done it.
Once a dark
It's always in you.
yeah, once a ranger, always a ranger. So.
It's true for the national parks and possibly for Babylon 5.
It's 7 o'clock.
Ooh, good luck with the tornado and severe storm warnings, Sue.
Yeah, where are you at,
yeah.
Sue? I heard that there were some in Pennsylvania earlier with the kind of the remnants of Fred. Well, let's go ahead and get started. And so hello, everyone, and welcome to the August NASA Night Sky Network member webinar. We're hosting tonight's webinar from, I'm in San Francisco, California at the Astronomical Society of the Pacific. And we have Dave in basically almost Canada and way up in New York. And we've got Cathy from Boulder, Colorado. We're very excited to present this webinar with our guest speaker, Dr. Cathy Olkin, the Deputy Principal Investigator for NASA's Lucy mission. And so welcome to everyone on YouTube. We're very happy to have you with us. These webinars are monthly events for members of the Night Sky Network. For more information about the NASA Night Sky Network and the Astronomical Society of the Pacific, in just a couple moments, I'll put some links into the chat. But before we introduce Cathy, here's Dave Prosper with just a couple of announcements.
Hi, folks. My announcements are a little stuffed tonight, so I'm going to try and get through this pretty quickly and clearly because I want to focus on the Lucy mission to the Trojan Asteroids. And I'm assuming everyone else here does too. So first, I got a fun item for everyone, just a hint. I just sent out the request to get our pins formally designed and manufactured. So the hint is the design this year may feature everyone's favorite rover helicopter duo, but that's not official until I get the final stamped pin. So look for official announcements in next month's newsletter. Just a reminder, we bumped up some of the dates on the pins when we did the date change last year. So I'm hoping to have them available for order from you all by September, October. So, and getting them out to you right after that. So more to come with that. Next newsletter. And we also have a big giant astronomy survey we want you all to take, and you may have already heard about it from us or someone else, but please, we would love, if you have not taken this yet, to take it and share it with anyone who might be interested. It's about 10 to 15 minutes of your time, but it is time well spent, because this is a sort of a state of amateur astronomy in 2021 survey, and it'll inform our next few years of planning with the Night Sky Network. And basically means we want to help better serve your club's needs. And to make that happen, we want to know what you think. And the survey is a great way to do that. And I'll stop talking about the survey and put the link in the chat so you can take it later, hopefully, and enjoy the talk now. And it is also at bit.ly/astrosurvey2021.
And we even want to hear from the people who aren't interested in taking it. Their feedback actually might be more important than all of you who are enthusiastic users of the Night Sky Network.
Actually, that'd be great. Send it to some folks that may have dropped from your club, but you're still hanging out with. Maybe get to know, ask them why, but ask them via the survey, so it's not awkward. Just a quick reminder too, if you're going to be posting any moon-related events on October, post them to your NSN club calendar soon, because International Observe the Moon Night is coming on October 16th this year. And if your club posts any public events in the NSN calendar between October 8th and 24th, with the word moon anywhere in the title, you'll have your events synced up with the event calendar for the International Observe the Moon Night folks and their setup. So you got to do this by September 1st to qualify for a packet of fun moon-related outreach materials to be sent to your club. So that's why you need you to submit the events by September 1st to give us time to ship these goodies to you for your October events. And if you don't want your events synced, just don't put moon in the title, or make it a club or private event only, and that will skip the sync process. The last thing, I may be seeing many of you at this, which is Alcon Virtual, which starts tomorrow, and it's free. It runs through Saturday and has some really excellent guest speakers and topics and guests like you and me. And you can join them for free on their streams at alconvirtual.org. And that is all from me. Back to you, Brian.
All right. Thanks, Dave. So for those of you on Zoom, you can find the chat window, and please make sure that you go down to the bottom, and Zoom fixed it. It now says everyone. If you've done an update lately, it now will say everyone instead of all attendees and panelists. And so make sure you select everyone so that everyone can see your greeting. You'll also find the Q&A window if you scroll down at usually on the bottom edge of your Zoom window on your desktop. That's where we want you to put all the questions that you have for Cathy during her presentation, and then we'll have time at the end that we'll be able to get to those. If you do have any technical difficulties, you can jot something into the chat, or you can always send us an email at nightskyinfo@astrosociety.org. And so with that, let me start my Okay, I want to welcome everyone again to the August webinar of the NASA Night Sky Network. This month, we welcome Dr. Cathy Olkin to our webinar. Dr. Olkin is a planetary scientist at Southwest Research Institute in Boulder, Colorado. Her main topic of research is the outer solar system, specifically planetary atmospheres and surfaces. She carries out ground-based observations to learn about the size and atmospheres of small worlds. She's worked on the NASA's New Horizons mission as the lead of one of the scientific instruments, the color camera and the composition mapper. NASA's New Horizons mission provided us with the first close-up images of Pluto and its moons in 2015. In 2019, the New Horizons spacecraft made the most distance encounter of any solar system object, Arrokoth, and I probably didn't pronounce that right. Cathy is also the Deputy Principal Investigator for NASA's Lucy mission. The Lucy mission will be the first spacecraft to visit the Trojan asteroids, asteroids that share an orbit with Jupiter. In her free time, Cathy mentors FIRST robotics programs, which I know many of you have done that as well. And so robotics programs are great, providing hands-on STEM education for students from 4th to 12th grade. And so having judged some FIRST competitions, it's a lot of fun, and I'm sure that Cathy's had a very rich experience with that. So please welcome Dr. Cathy Olkin.
Hi, everyone. I'm delighted to be here today and to tell you about the Lucy mission. So let me show you some slides about Lucy. All right.
Looks great.
Thank you. All right, so today I'm going to tell you about NASA's Lucy mission. This is the first mission to the Trojan asteroids. So we've never sent a spacecraft to the Trojan asteroids before, and this is going to be a first. So I can't wait to get there and see what these objects look like. First, a little overview. Lucy is a Trojan tour. It's a robotic spacecraft that travels out to the Trojan asteroids, and we're going to fly by 7 different Trojan asteroids through the years 2027 to 2033. We actually are going to launch in October of this year. The spacecraft is down in Florida at Cape Canaveral, getting processed right now and getting ready for launch. And it takes a long time to get to the outer solar system. And on our way out there, we're going to do a rehearsal at a Main Belt Asteroid in 2025. So that's what we have coming up. And we're going to fly by these objects and learn about them as we go. And I'm going to tell you some about the motivation and what we'll be learning about these Trojan asteroids. And I should say here, for those who are maybe not familiar with Trojan asteroids, that in this top-down view of the solar system, you see the sun in the middle, and then the inner planets, and Jupiter is the outer kind of orange circle. The green dots are the Trojan asteroids. They are in 2 swarms, one that's ahead of Jupiter in its orbit and one that's behind Jupiter in its orbit. These are the L4 and L5 Lagrange points of Jupiter. And these are stable zones. So if you put an object there, it will stay there. And there's other Trojan asteroids as well. Some other planets like Neptune have known Trojan asteroids, but this mission is going to the Jupiter Trojan asteroids. So the science motivation is really kind of twofold. The first one is to boldly go where no one has gone before. As I said before, we've never seen one of these objects close up. And we really want to understand what they look like and what their properties are. And part of the reason we want to understand that is because these are the leftovers, the remnants from solar system formation. Their near neighbors might have gone into making up the giant planets. And so we want to look at these objects to really understand what these building blocks of solar system formation were composed of. And the Trojan asteroids are a really interesting population because they're not homogeneous. As you saw in the last figure, they're located in a very confined area in the solar system right now. But we think that might not have always been the case. And they have a pretty significant variety of albedo, or the reflected light from the surface. Here in the bottom left, you see the visible albedo versus a 3 micron WISE mission albedo. And the albedos really range from 4 to 15%. And then if you look at their spectral slope, so this is an indication of color in the visible, there's 2 specific, it's 2 different populations, a red population and a less red population. And so it's not just a random distribution, there's 2 distinct populations. Also, in not being a homogeneous population, they have different spectral types. The different spectral types really tell you about the spectrum as a function of wavelength from about 0.45 microns out to 2.45 microns. This is a region from the visible into the near infrared. And there's a taxonomic classification system. There's been a number of them. One of them is by Buss and DeMeo. And this classification system basically is a way to look at the surface properties. And they have different reflectance as a function of wavelengths. As you can see over on the left here, there's C types and D types and P types, and they have different slopes in this spectral range. And we have those three types of asteroids present in the Trojan swarms that I showed you before. And you could imagine perhaps if the Trojan asteroids formed in the location they're at today and had their whole existence there, they would have formed out of the same materials and they would have been processed in the same way. So you would expect them to be more homogeneous. And instead we see these different spectral types. We see, and the different spectral types depend on what size the objects are. So in the 20 to 50 kilometer size range, you have mostly P's and D's with a little bit of C's. And in the 50 to 100 kilometer size range, you have mainly D-type asteroids. And in the greater than 100 kilometer, it's P's and D's. And these are basically telling you about the different surface features on the surface composition on the Trojan asteroids. And this diversity is really the result of accretion and the evolution in the outer planets. There's theories that the solar system as it was forming, that the giant planets migrated outward away from the sun, and they reached a resonance, a 2-to-1 resonance, where Jupiter would go around the sun twice for every one time that Saturn went around the sun. And this resonance caused a chaotic disruption of the small body populations in the solar system and would have ejected some small objects away from our solar system and some from the outer solar system into the inner solar system. And that's one possible explanation for how the Trojans became located where they are today. And so one of the goals of the Lucy mission is really to understand the diversity of these Trojan asteroids so that we can learn about their history. And these are the targets that we're going to go to in order to learn about the diversity of these objects. We have 5 objects in the L4 swarm, that's the one that leads Jupiter in its orbit, and 2 in the L5 swarm. I'll tell you a little bit more about these objects, but you can see the coloration. So first of all, I'll say that these are artists' conceptions of what the asteroids look like. We don't have anywhere near this level of surface detail about what the Trojan asteroids look like. That's why we need to send the Lucy spacecraft there so that we can see how many craters on the surface, what does the geology look like, and what kind of variation in the surface color and composition exists. We do know that Lucas and Oris are both D-type asteroids. Remember, I showed you the spectral types before. They are more red than the other objects in our sample that we'll be visiting. And then there's P-type, or kind of primitive objects, and that is Patroclus Magnesius and our small object Polymele. And then there's Urabades and its small satellite Keta. So Urabades is a pretty interesting object. This is going to be the first one we fly past, and it is a remnant from a previous collision. We can look at the orbits of Trojan asteroids and also Main Belt asteroids and identify families. Families are a group of asteroids that used to be one object that was then disrupted, and those pieces didn't coalesce back together but went on their own independent orbits. And so from the orbital elements, you can look and understand which asteroids had this history, was a collisional family. And the only collisional family in the Trojan asteroids is the Urabades family. It's named after the largest remnant from that disruption, the one that we're going to visit. And here is a simulation of what that disruption might look like. You can see the how the objects coalesce in the rightmost panel. So that's going to be a very interesting object to go visit. And then I want to call attention to Patroclus and Magnesius. This is a really interesting pair of objects. They orbit each other. So they orbit a common center of mass between the two of them. And you can see the animation, which is once again an artist's conception of what the objects would look like, going about their common center of mass. And the scale of the size of Patroclus Magnesius relative to its orbit is correct in this animation. And I really wanted to point out the little inset box here that says Hubble Space Telescope, HST, on the right, because that's what the data looks like that we have on these objects. So when I said before that these are artist conceptions, you can see how much liberty was taken in showing you what these objects might look like from what we really know, as you can see from the Hubble Space Telescope images. And I wanted to share, since this is the Night Sky Network, I thought you would all like seeing the way that astronomical observations inform the mission planning. So we have made extensive use of ground-based observations, particularly occultations and light curve data. So photometry from the ground, looking to see how the light varies with time that we see from our Trojan asteroids. And right here, I'm showing you one of our targets. It's called Lucas. It was one of the more red ones that I showed you previously. And before we started this campaign of stellar occultation observations, of which we've had 5 events that have been well observed, I'm showing you 4 of them here, we didn't have a good shape for what Lucas looked like. So we really wanted to understand that. And it was important to understand the shape of Lucas because it's a very slow rotator. It takes about 400 hours for it to rotate on its axis. And as you do a planetary flyby, that means we're not going to see one side of Lucas as well. So to really understand the mass properties of Lucas, we need to get solid understanding of its shape from the ground. So we've invested a lot in stellar occultation observations of Lucas. And like I said, also combining that with light curve data. And you can see these are stellar occultation light curve chords. So each line here is an observer in the path of the stellar occultation. So we're watching Lucas pass in front of the star. And you can see the dots on the lines, which are where the light dimmed out as Lucas was passing in front of the star. And if you can see really carefully, there are little ticks there that indicate the uncertainty in that time of where the light curve the flux from the combined light of Lucas and the star dropped to just the light from Lucas. And so we have all of these great chords. You can see this event, which was really well sampled here. And from this data, we're able to fit a shape model of Lucas. And this is on the right here is the shape model showing you from different views of what we believe Lucas looks like. And we could still get very surprised when we fly past, because this type of modeling only gives you convex shapes. So concavities, you really can't get from this retrieval method. And you can see the resolution of the facets that we've used to fit the data. And if any of you are interested, this is described in a paper by Matola et al. That was published in 2020 in the Planetary Science Journal, and that is open access for anybody to read. And this data, the light curve coupled with the occultations, allow us to estimate where Lucas's spin pole is. And so you can see a probability map here, or a chi-squared map showing the likely location of the spin pole where you have the darker colors. So before this, we didn't know the axis that Lucas rotated around. So we're learning more and being able to constrain that better and getting a better shape, all from astronomical observations. And I wanted to share some of these pictures with you. These are pictures from our team in the field, and two of the people who've been helping with our stellar occultation observations are Night Sky Network members or coordinator, Christopher Erickson and Roxanne. You can see them here. And I saw that they were online tonight listening to the webinar. So good to see you virtually. And they've been participating in our stellar occultation campaigns. Next, I want to show you the trajectory of the spacecraft. We launch on October 16th, 2021 on an Atlas V 401 from Launch Complex 41 at Cape Canaveral. And this is the type of rocket that we will be launching on. And we orbit in a 1-year orbit about the sun and come back and do an Earth gravity assist just about a year later. And the actual exact details of our first Earth gravity assist depend very much on when we launch in our launch period. So this is a demonstration of what it would look like when we launch on the first day of our launch period. And we have a very sporty EGA. We're flying just 300 kilometers from the surface of the Earth. So under the space station, under many satellites. And so this will be a sporty flyby. And that allows us to increase our aphelion, and we go out about twice as far away from the sun as we had been previously. You can see there, and now we're coming back closer we're gonna come back towards the Earth. When we're at aphelion, we actually do a burn that allows us to slow down. And this will increase our velocity when we fly past the Earth at EGA 2. Orbital mechanics are a funny thing, the way things work. You slow down to go higher, and it has lots of different implications. So we have a second Earth gravity assist in 2024, and this will allow us to boost our orbit all the way out to the Trojan asteroids. So now at this point, we're going about 34,000 miles per hour, which is about 19 times faster than a bullet. So we're really cruising by the Earth very fast. And then we do a flyby of a Main Belt asteroid. This is a small Main Belt asteroid. It's probably about 5 kilometers across. And we will fly by in 2025. And what we're doing at Donald Johansen, that's the name of the asteroid, is a rehearsal. We're going to be rehearsing for the Trojan asteroid flybys that are to come. We want to make sure that everything on the spacecraft works the way we expect. We've done many systems level tests here on the ground. We will do lots of tests in flight, but there's nothing like an actual flyby to test and make sure that we have got everything working the way that we want it. Donald Johansen is also an interesting scientific target as well. Remember, I told you that Urabades was a collisional family member? Well, Donald Johansen is as well. So this is a remnant from a previous collision. It'll be very interesting to see what it looks like. And the last thing I'll tell you is that we were able to name this asteroid. We named the asteroid after the discoverer of the Lucy fossil. This is an Australopithecus fossil that was found by Donald Johansen and his team back in 1974 in Ethiopia. And the Lucy fossil that you can see in the upper right of my slides, that is really transformed our understanding of the evolution of hominids. And just like the Lucy fossil transformed our understanding of human evolution, we plan to have the Lucy mission transform our understanding of solar system evolution. So we're going to fly by Donald Johansen, and that from there we go out to the L4 swarm. I'm only showing you selected objects in the L4 swarm, just the ones that we're going to fly by. So there's many other objects in the area. And even though I say there's many objects in the area is very large. So we're not worried about hitting one accidentally. From here, we get to fly by our first Trojan asteroid target. And this is Urabades and its small satellite Keta. And we're gonna fly by in 2027. So we launched the mission in October of 2021, and it's gonna take almost 6 years to get to the Trojan asteroids. So we have to be very patient to get there, and exploring the outer solar system takes a lot of time. After Urabades, just 30 days later, we fly past Polymele. This is another one of our targets. It's one of our smaller targets. I'm excluding Keta because we're targeting the flyby of these larger objects. And we're gonna fly pretty close to Polymele. We're gonna fly about 600 miles away from most of our targets, but Polymele is smaller. And so we'll be going closer, just 270 miles away at closest approach. And the reason we're doing that is so that we can kind of weigh the Trojan asteroid by measuring the Doppler shift of the spacecraft as it flies by. And I'll tell you more about that in a little bit. Next, we fly past Lucas, and that's the one that I showed you the occultation light curves of. And about 7 months later, we fly past Orus. And this is our last of the L4 Trojans. From Orus, we fly back and past the Earth again. We do another Earth gravity assist. And this Earth gravity assist sets up our aim point to get to Patroclus and Magnesius. Patroclus and Magnesius are the final targets in our prime mission. You can see them here. And that flyby occurs in 2033. So quite a long time from now, but it's going to be so exciting to see what these objects look like. And then from there, we just continue out and we continue circling in this manner inward and then back out to the Trojan asteroids. And we'll be transmitting our data all along, but the Trojan, the Patroclus and Magnesius data will be the last data that comes down in our prime mission. So now I want to turn and tell you a little bit about the hardware that we have. We have this beautiful spacecraft you see on the right, and it has on the top of it an instrument pointing platform. And that instrument pointing platform is attached to the spacecraft with a 2-axis gimbal. It has a large range of motion. Basically, it can point down back towards the spacecraft and then all the way over and towards the high gain antenna that you see here. And it has a small range of motion in the cross track direction. So the way it can rock kind of towards one of the solar arrays, either one of them. And the scientific instruments mainly sit on this instrument pointing platform. We have a high resolution imager called LORRI, and this is very similar to the LORRI instrument on New Horizons that brought you the highest resolution images of Pluto. And next to LORRI, we have 2 terminal tracking cameras. These cameras are part of our guidance, navigation, and control subsystem, and they allow us to track the asteroid with the pointing platform. So to take images and then line up our instruments so that we're pointing at the Trojans the whole time we fly past. We're flying past at between 6 and 9 kilometers per second. So that's very fast. If any of you have run a 10K race, that's like doing it in just a little bit over a second, which is crazy. So we're going to fly by really fast, and we need to keep our instruments targeted on the Trojans as we do that. LTES is this instrument right here, and it's like a remote thermometer. It allows us to get the black body curve in the infrared, which allows us to determine the temperature of the surface of the Trojan asteroids. And we're interested in understanding the temperature at different times of day so that we can understand the properties to retain heat in the regolith on the asteroids. And then on the furthest right in our instrument pointing platform, we have this big behemoth of a instrument here called the Ralph. It is a color camera and infrared imaging spectrometer, and it's based on the Ralph instrument on New Horizons. So it'll be what gives us our color and composition information. And the radio science, we'll be able to do a radio science experiment, like I mentioned previously, where we can look at the Doppler shift of the signal as the spacecraft flies by to get an estimate of the mass of our Trojan asteroids. So we're going to do a geology investigation, and the geology is really going to provide data on the shape of the target, how many craters there are on the surface, and what are the characteristics of the surface. Do we see mass wasting or mass that's slumping downhill in a crater? What type of ridges do we see? And that can tell you about the internal structure on the Trojan asteroid. And all of these data that we're looking for from a geologic standpoint are diagnostic of the history of these targets. And here you just see three very different examples of small bodies in the outer solar system, or in the solar system, from a main belt asteroid to a comet to a small moon of Saturn. And this is a mosaic of asteroid images that was put together by Emily Lakdawala. And these are basically all the asteroids that we've flown by and have close-up images of. And the asteroids are approximately to scale, and the surface brightness that you see for them is also to scale. So over here you can see Matilda, and that is very dark, and Lutetia, that Rosetta flew by, the Rosetta mission flew by, is much brighter. And our Trojan asteroid targets span the size from approximately Lutetia, which Patroclus Magnesius is about that size, down to the size of Dactyl, which is a small satellite of Ida. And Dactyl is about the same size as Keta, the satellite of Urabades. So we're going to be spanning a wide range of sizes and really being able to look at very different objects across the Trojans. In surface composition, we're going to be looking for clues to where the Trojan asteroids formed and what chemical processes might have affected them. So you can see this diagram here in the bottom left shows you the formation distance in AU, where an astronomical unit, 1 is the distance between the Earth and the Sun. And so you can see where Jupiter is here, and Saturn and Uranus, Neptune, and Pluto. This is the average Pluto distance because it has an elliptical orbit. And these molecules all here, you can see where they get retained or lost. And so it's a function of the size and where they formed. So we're going to be looking for things like water and CO2 and different molecules to understand the history of the Trojan asteroids. We'll also be able to investigate minerals on the surface like olivine, pyroxene, and serpentine. And that tells you something about their formation and whether they differentiated. You can see a differentiated body down here. And the way we do this is by taking spectra. We'll be taking spectra. We'll get visible images here out to about 1 micron, and then we'll get spectra out to about a little bit past 3.5 microns. And you can see all the different species or molecules that have absorption features in this wavelength range. And so this is how we're going to be looking for the fingerprints of these molecules in our spectra. And the the reason they have these different dips and undulations in the spectra have to do with the modes of how the molecules move. You can see the vibrational modes in water, and you can see 3 different modes shown here, and each of them is diagnostic of a different wavelength. And when we look at the Trojan asteroids from the ground, we see spectra that look like this. These are 2 different examples of a more red and less red Trojan asteroid, and they're featureless. Generally, there's some features out near 3 microns, but when we get up closer to the Trojan asteroids with Lucy, we'll be able to look at smaller regions on the surface. And that will allow us to look and not be swamped by the overall signature from across this whole object, but we'll be able to see if there's differences in the surface composition across the object. And that's something that's not possible at all from the ground. And these are some examples from the Dawn mission looking at water exposure or organic materials, and you can see where they can be mapped across the surface to understand how the geology and composition work together. Next, I want to talk about satellites and rings. As I mentioned previously, we discovered this small moon Keta using the Hubble Space Telescope. And if we assume the same albedo or surface reflectance as Urabades, we estimate that Keta is about a little more than a kilometer across. So like I said before, about the size of dactyl. And we have a pretty decent orbit for Keta, given that we just discovered this small satellite. And maybe it's probably not surprising that Urabades has a satellite. As I showed you before, we believe that Urabades is a member of a family-forming collision, and there are examples of how satellites could form in such collisions. In addition to being able to look at Keta, because we've discovered it well in advance, we're going to be searching for satellites and even rings as we approach the Trojan asteroids with Lucy. So there may be more satellites waiting to be discovered. So here is the uncertainty in Keta's orbit shown in red. And what you see here are 2 different plots of the Lucy trajectory in blue. The one on the left is looking down from the pole of the solar system. You're looking down, and then the other is looking sideways. And you can see how the uncertainty in Keta's orbit is quite large, even though we have a pretty good orbit, given it was just recently discovered and how faint it is relative to Urabades. But we're going to be flying pretty close by, but we won't hit it, as you can see, because over in the right panel, we're going to be flying under this, the location where it is at some point. It's going to be somewhere in this ellipse. So we're going to continue to improve our knowledge with more observations of Keta so that we can shrink this uncertainty cloud. And I want to tell you a little bit about naming this small satellite. Because we discovered it, we got to suggest a name. And the Trojan asteroids are generally named after characters from Homer's epic poems. But given that there are only so many names in Homer's work, the IAU has allowed that now we can name small Trojan asteroids after Olympic athletes. And so we've named Keta after the first woman to ever light the Olympic torch. And she did this at the 1968 Olympics in Mexico. And her name is Enriqueta, and her nickname is Keta Basilio. And so we named the satellite after her. And it was really very fitting because the character Urabades in Homer's poems was a herald. And the modern Olympics, that role is reenacted with the lighting of the Olympic torch. So we really liked all that symbolism coming together. And We're also going to be measuring the mass of the object of the Trojan asteroids using our high gain antenna, which operates using just 100 watts of power. And by carefully looking at the Doppler shift, we'll be able to retrieve that mass. We're going to get the mass to better than 25% for all of our targets, much better for a number of them. The larger ones will be pretty easy. And using the imagery data that we have for shape, we'll be able to determine the density. And there's reason to believe that perhaps the Trojans might be very underdense, so maybe even less dense than water ice. And to give you an idea how big the Lucy spacecraft is, from tip to tip with the solar arrays fully deployed, it's 47 feet. And that's about the size of a large semi-tractor trailer. These are the instruments on board the instrument pointing platform. I showed you the CAD model before, but I want to show you the real thing. And this picture was taken at Lockheed in Littleton, Colorado. You can see a person, he's kneeling, but to give you an idea for scale, the person is here. And so you can see the instrument pointing platform with all the instruments being prepared for the spacecraft. And we do tests. We test a lot of testing. You want to fly as you test and test as you fly. And so you can see a deployment test of the solar arrays. So our solar arrays are furled up and very flattened. They're only about 4 inches wide when they're fully closed up. And we need this configuration for launch to fit in the fairing of the rocket. And then we deploy the solar arrays kind of like a Japanese fan, and they unfurl. And this was a test of that unfurling that took place. And you can see all the metal structure and the lines supporting the solar arrays. That's because they weren't meant to deploy under 1G of force. So that is a structure used to offload that weight, so that we can test on the ground before we get into orbit. And I encourage you to follow the Lucy mission. We have a Twitter channel and Facebook and Instagram, and there's both the NASA website and the Lucy Project website. And this is our cartoon character of Lucy on her journey. So please feel free to follow us and see what's going on with the Lucy mission. And from here, I'll stop and take your questions.
All right. Well, that's really fantastic. And so maybe we could, Dave's got the information in the chat. So we might want to come back to a couple of the slides, or maybe put that one back up later on so that people can see it. So we've got some good questions here. And so very early on when you're talking about the different planets, and so Paul wonders, does Earth have Trojan asteroids as well?
So that's an interesting question. In the OSIRIS-REx mission, the one that went to Bennu and got a sample and is bringing the sample back now, they were searching for Trojan asteroids. There are some objects that look like maybe they get captured for a short period in Trojan, the Earth Trojan points, but I don't think there's any long-term known Earth Trojans.
Well, hopefully before too long, we'll have our own Trojan JWST.
That's right. That is true. At Earth, so there's more than just the L4 and L5 point. There's other Lagrange points, 1, 2, and 3. And so 1 and 2 could be used to put spacecraft in, and that is where the JWST will be going, which will be very exciting. Right. And the reason it goes there is because it's easier to do station keeping, because it's a stability point.
Excellent. Okay, so John had a question, and I'm going to have to see if I can, understand this entirely. So I think that he's asking, so we have the Main Belt Asteroids and we have the Trojan Asteroids, and so he's asking about the percentage of Trojans. Maybe it has to do with the types. Does it match up with the numbers and the percentages in the Main Belt Asteroid, or what are the sheer numbers like? What are we talking about? How many?
Yeah, so right now there's a little more than 9,000 known Trojan asteroids, but we believe that there's hundreds of thousands of actual Trojan asteroids, many of which we haven't discovered yet, just from looking at size frequency distributions and projecting what should be out there. I'm very much looking forward to the Vera Rubin Observatory coming online, because many more Trojan asteroids and other small bodies in our solar system will be discovered with Vera Rubin when it's online. And so the question about basically types of asteroids compared to the main belt, you see a gradient in the main belt asteroids of spectral types, and you see basically different, you don't see the same types of Trojan asteroid distribution of spectral types as you do throughout the main belt.
So that one graphic that you showed with the little pie charts, those would look significantly different for the main belt asteroids?
They would. They'd look different for the main belt asteroids, and they'd look different at the inner part of the main belt versus the outer part of the main belt.
Okay, because I was wondering, and this was, I guess my question is that I was looking at that, and in the description it noted that the least common type that you had in the Trojan asteroids were the ones that we've actually sampled. And so I was wondering if the compositional percentages held true there as well, or is it that we're sampled the least prevalent types?
So that's a really good point, is that we don't expect that we have any samples of the Trojan asteroids in our meteorite collection, because they are generally constrained in those Lagrange points. So they're not coming in and impacting the Earth. And so that's another reason to send the Lucy spacecraft there, is because we don't have a sample from the Trojan asteroids in our meteorite collection. And it is true that basically when you look, you see a lot more C types further in the asteroid belt.
Okay, great. So Michael asked, will the spacecraft be visible to amateur astronomers at any of the Earth passes, or particularly the closer ones? So.
Yes, and I expect that at EGA1 that Lucy will be visible as it flies by. We've got a large area, and there's going to be a point in time when it'll be in dark sky but still illuminated by the sun. And I look forward to sharing that with the amateur community and the professional professional astronomer community as well, because I think it'd be really exciting to take a picture of Lucy flying by, and also for us to go out and look. I think it might be a visible sky object perhaps as well. But as I said before, the exact altitude and circumstances of our first Earth gravity assist really depend on when we launch in the launch window. The altitude goes up as we get later in the launch window. So after we launch, I can let people know.
All right, thank you. So Richard has an interesting idea, and so he wonders if the redness of the asteroids might be coming from the Io volcanoes, or whether there's some sort of interaction that's going on there.
Yeah, that's an interesting question. So Io is really far away. The closest that Lucy gets to Jupiter is actually just after one of our Earth gravity assists. And that's one of those things that's hard to fathom. It's just that, Jupiter's orbit is very large, and the Trojan asteroids are quite far away. So they're associated with Jupiter because they share an orbit, but they're nowhere near each other. So the red color would not have to do with Io at all. It could have to do with space weathering. So over time, you can perhaps get reddening, but then some people have seen some evidence that things can get more blue over time with cosmic rays and irradiation. So I think it really depends. It's a combination of what materials you start with, and then how you weather them impact from cosmic rays or solar radiation. So there's a lot of interesting work still to be done there.
So many questions.
That's right. I love that though. I mean, that's the whole point of this. When I was a kid in school, you know, I learned science from my books, and so often I learned what we knew, but not what we didn't know yet. And I think it's just really important for all of us to keep in mind what we don't know and where all these questions are. And because each question that we eventually get an answer to is going to spawn even more questions, which is lovely.
So are you hoping for questions that you don't know that you have yet after Lucy gets out there?
Oh, I hope so. I think that would be great. I'd love to have a new set of questions I didn't even know to ask before.
There you go. So speaking of questions, and so Paul asks, what makes scientists think some of the asteroids were formed or affected by collisions? And so, you know, what kind of things are you seeing?
Yeah, we see craters on the surfaces of many objects that we across the solar system. You know, the moon, asteroids. So I would expect that we would see craters on the Trojan asteroids. And in fact, we have a science objective to map the craters over 2 orders of magnitude in size. And the reason we want to do this is so that we can understand the age of the surface. By looking at the cratering rates, you can get an idea of how young or old the surface is. There's different models for how many craters you would expect to see over time at different parts of the solar system. Craters are the remnants of an impact. And if you have a large enough and energetic enough impact, you're going to have catastrophic disruption. And we can see evidence of disruption like that in these asteroid families. So there's lots of interesting evidence for collisions throughout the solar system.
All right, thank you. So let's see, we've got, so we were wondering, we had a question, can you compare the LORRI instrument on Lucy to the one on New Horizon?
I can. They're almost exactly the same. They have the same aperture, they have the same detector. Let's see, with the LORRI instrument on Lucy, we added redundant electronics and some data, some capacity to store the images. So on New Horizons, the data from LORRI go directly to the spacecraft. On Lucy, they'll go onto a recorder that's part of the LORRI instrument and then be transferred to the spacecraft. But you know, optically, it's really the same. And yeah, so it's going to be great because LORRI was great at Pluto.
Well, we certainly were delighted at all the images that we got back from there. And so we've got something really good to look forward to. So.
Yeah, and we'll be using the LORRI instrument on Lucy for optical navigation, just like we did at Pluto.
Excellent. Okay, so Stephen notes or asks the density of Quetta, 1 gram per cubic centimeter. And so are you indicating as ice or water? What's the indication that you're thinking?
Well, so I'm not sure what the density of these objects will be, but there are some measurements of Trojan asteroids and their densities based on binary systems that would lead you to believe that they'd be less dense than 1 gram per cc. And so it'll be interesting to see what we find. And there tends to be a general trend across the solar system that things are less dense further out. And so that'll be another indication perhaps of where these objects formed.
Okay, so let's see what we got here. Okay, let's go up to this question. And so Randall asks, will the spacecraft have thrusters to enable you to adjust the trajectory as it approaches the Trojans?
It does. we have a biprop system on the spacecraft, and we can do large maneuvers like deep space maneuvers where they're much more velocity change, and we can do small maneuvers. We have smaller thrusters for that with hydrazine. And we have planned a trajectory correction maneuver 30 days before we get to the Trojan asteroids, and then another one 7 days before we get to the Trojan asteroids, so that we can hit that aim point that we're going for just right. And so that's definitely part of our plan. And that's why we need the optical navigation as well as the radiometric data types, so we'll get through the deep space network.
Okay, so back to the LORRI instrument then for a moment, since you brought that up again. And so so we have a question. So we can probably expect more detailed images of the Trojans, since Lucy will be closer to them than it was to Pluto. Is that?
Yes, yes. And so the highest resolution that we have requirements for the science images that we plan to take to accomplish our science objectives. And the highest resolution one is tied to that imaging the crater populations that I mentioned. And so we expect to get 14-meter resolution so that we can map craters down to 70 meters in diameter. You want to have multiple pixels per crater to be able to identify the crater. And we were conservative in saying we want 5 pixels across. So 14-meter resolution, which is in fact higher resolution than New Horizons.
Okay, we're going to go for 2 more questions here, and then we're going to call it good. I apologize to those that were not quite getting to your questions. So Kriya asks, are the instruments on Juno completely powered by solar power? How large is the solar array? I know you showed us the graphic with the semi-truck. How does that compare with Juno, since they're basically at the same distance from the sun?
Yes, so the solar arrays are 7.2 meters in diameter. I don't know what the area comes to off the top of my head. I should look that up, but you can get a rough idea from the 7.2 meters in diameter. The Juno spacecraft solar arrays are actually larger in area than the Lucy ones are. And that's because the Juno spacecraft needed more power than the Lucy spacecraft does. The Lucy spacecraft will be the furthest operating spacecraft from the sun because we go a little bit further away than Juno is from the sun.
All right, so last question here. And so John, it's a different John. And so we've got about 4 different Johns that we've had questions today. I should have numbered them all.
And we have more than 4 different Johns on the project too. Very popular name.
So this John says, what happens to Lucy after 2033, or when the planned portion of the mission ends? And I think you had one graphic that kind of alluded to that, but what's the plan for data acquisition and things after that?
Yeah, so after that, Lucy will continue on, and it will sweep into the inner part of the solar system and then back out to the Trojan clouds over and over again, the Trojan swarms. And so, I look forward to putting in an extended mission proposal 2033 and hopefully be able to continue doing science on the Trojan asteroids. We put a plaque on the Lucy spacecraft, and that plaque is a plaque to our future selves. You know how the Pioneer and Voyager spacecraft had plaques because they're leaving the solar system. And so, some civilization not in our solar system could potentially find those plaques and read them. Well, the Lucy spacecraft is going to stay in our solar system and rattle around for a very long time. So we put a plaque on there for future explorers in space. And we had quotes from many different poet laureates about basically what they would say to our future selves. And so I think that's kind of a fun thing to think about, Lucy being out there. Yeah, and I should mention that, so Lucy's named after the fossil. The fossil is named after the song, Lucy in the Sky with Diamonds. And we actually have a diamond on the spacecraft because one of the optical elements in the TESS instrument is a cultured diamond. It's a beam splitter for our interferometer. And so we will be taking Lucy to the sky with diamonds.
Oh, very cool. I love it. All right. And so thank you, everyone. And thank you, Cathy, for joining us this evening. And so you can look forward to our next webinar on Tuesday, September 21st, when Dr. Paul Abel will share with us NASA's plans for the DART mission. Here's another asteroid mission. This one will demonstrate a potential technique for actually changing the motion of one, which would be kind of an important one for things that aren't stuck in a Trojan position. We kind of want to know what to do with those at some point. So also join us on Wednesday, September 8th, when Andrea Jones will return to help us prepare for this year's International Observe the Moon Night. All of these webinars you can find on the Night Sky Network website in the Outreach Resources section, and you can also find them on the Night Sky Network YouTube channel. So keep looking up, and we will see you all next month. So good night, everyone.
Bye, everyone. Thank you.
Thanks for joining us all.
And thank